Welcome back. Now that we're done with the formalities, let's start doing what we actually came here to do. Let's talk about galaxies. In this lecture, I am going to start with taking a little historical overview of how we found out that galaxies exist and that the Milky Way is but one such galaxy out of a virtually infinite number of galaxies in the universe. Back in the 17 and 1800s, we got better and better telescopes, and they allowed us to better study the objects that we found in the night sky. It had been known from before that the night sky was full of stars, of course, and planets, which looks a lot like the stars, except they move compared to the stars, which in their turn are more or less fixed relative to each other, and therefore were called the fixed stars. But on top of that, there were also a few blobby, fuzzy objects that kind of defied categorization among the stars and the planets, and these were called the nebulae, nebula simply being the Latin for a cloud. Most famous, of course, is the Andromeda Nebula, which we today know to be a galaxy on the northern sky, and the Magellanic Clouds on the southern sky, which also are visible with the naked eye, which we also today know to be satellite galaxies of the Milky Way. But as we got better and better telescopes, we found that there were more and more of these nebulae sitting and hiding in the night sky. And it became a little bit of a mystery what these nebulae were. And people started getting interested in the nature of these nebulae. The philosopher Immanuel Kant, which people probably primarily know for his moral philosophy and his categorical imperative and all that, but he was also a natural philosopher. He suggested back in the 1750s that the nebulae were island universes, that the Milky Way was just one of such island universes, and that it looked the way it did to us because we were inside it and not looking at it from the outside like we were with the others, which is a surprisingly accurate depiction of how things actually turned out to be. But it is important to note here that Kant had a very good intuition, and he had a very strong philosophical basis for making his conjectures, but he didn't actually have much by means of scientific evidence for his theory. It was not at Kant's time possible to scientifically confirm or reject his hypothesis, and wouldn't be for another 150 to 200 years. Still, it was quite a remarkable feat to come up with such an accurate depiction of how things actually work at such an early time in history. A bit after Kant's conjecture about the nebulae, the astronomer Charles Messier was compiling his catalog of the comet-like nebulae. Charles Messier was actually mainly interested in studying comets, and he got more and more annoyed that he found these pesky false positives, nebulae that were kind of imposter comets, nebulae that were looking like comets, but they weren't real comets. And so he compiled this catalog of nebulae that were not comets in the beginning, originally, basically to know where they were so that he wouldn't get all worked up that he had discovered a new comet and then figure out it was a false positive again. But yeah, and one man's trash is another man's treasure. I think the Messier catalog today is one of the most astonishing legacies of the science of that era. We still use it today, and basically all the grand design galaxies that we see on the pretty pictures from Hubble or the James Webb Space Telescope or so on are part of the Messier catalog. They all have these catalog numbers starting with an M and a number. the Andromeda Galaxy, its companion galaxy, and so on, all have Messier numbers. Fast forward a little less than 150 years. Not a lot had happened in the meantime, science-wise. There had been some incremental progress, not least in terms of the quality of the observations people could do. But basically, we still didn't have any hard evidence that could finally settle the nature of the nebulae. And in around 1920, there was what we call the Great Debate between two camps led by Shapley and Curtis. And basically, one camp held that the universe, or the Milky Way, was the entire universe, and that the nebulae were simply just small nebulous objects inside the Milky Way. And the other camp held that the Milky Way was just one of such infinite number of nebulae, and it looked different to us because we were inside it, as Kant had been suggesting before. It's interesting to see that actually both camps were right in a way. Many of the nebulae of Charles Messier's catalog are actually supernova remnants or planetary nebulae or something like that inside the Milky Way. But many of them are galaxies that are far away and are as big as the Milky Way or even larger. So even though the old-timer camp had a point, I think you would still say that they lost the debate in the end. And the way they lost the debate was not because they were better or worse at debating, but because we got better observation techniques and we got better evidence. In 1923, Edwin Hubble found a Cepheid variable in the Andromeda Nebula, and that way he could establish that it was indeed the Andromeda Nebula, a galaxy of itself. It was indeed an extragalactic object, not something that sat inside the Milky Way. The way this works is that Cepheid variables is a class of stars which are pulsating in brightness rhythmically with a very regular period, and this period is quite tightly correlated to its brightness, like its base brightness. Which means that once you have found the period of a Cepheid variable, you also know its intrinsic brightness, and you can then compare that intrinsic brightness to its observed brightness and use that to find the distance to the star. And that's what Hubble and his friends did back in the day, and they found that this Cepheid variable simply was way too distant to possibly be a part of the Milky Way. And I think that is an important point to dwell a little bit on. That a lot of our progress in astronomy is driven by better, steadily improving observing techniques and technologies. What we see here on this slide is 4 different renditions of the galaxy M51 or Messier 51, which is actually 2 galaxies, 2 interacting galaxies. It is also known as the Whirlpool Galaxy. And the first thing we saw is a drawing made by William Herschel through his, by then, modern, but by our standards, hopelessly obsolete handheld telescope. And we then see, of course, they also didn't have any photographic plates or anything back then. So all that they could do was that they could look with their eye through the telescope, and then they could make a drawing on paper as faithful as possible to what they saw through the telescope. We see 2 examples of that from Rossi in 1845 and Rossi in 1850. You can basically see that his observational instruments are getting better. And then we see, finally, to the right in panel D, we see, maybe I should do a little pointing here. This one, yes. We see that there is a lot of we see this image taken with the Hubble Space Telescope back in 2008. Since then, this galaxy has, of course, also been observed with the James Webb Space Telescope, which gave us yet another step up on the ladder of detail and accuracy of these observations. But it is quite cool to see just here how much detail we can see in this image compared to the others from before. Now we need to take a step back and look at something else, which is stars in galaxies. Galaxies are largely made of stars, and in particular, the light we see from galaxies is almost exclusively starlight. And that means that all we know about galaxies, we actually know from observing and interpreting the integrated lights from billions upon billions of stars from these galaxies. That also means, of course, that if we are to understand galaxies properly, we also need to understand stars. Now, this is not a course in stellar astrophysics. This is a course in galaxies, and you are expected to have a fundamental knowledge of stars before starting this course, but just to make sure that we are all on the same page, it doesn't harm to do a quick little review. Basically, there are two kinds of stars. This is not entirely true. This is ignoring an entire plethora of a huge variety of stars that actually exist. But those stars are rare. By far the most common stars there are the dwarf stars, such as the Sun, and the giant stars. And these differ both in mass, in radius, and in the luminosity. Dwarf stars are, generally speaking, main sequence stars. It means that they are stable, they are hydrogen burning, they are not evolving very rapidly. On the other hand, giant stars are typically evolved and inflated stars at the end of their life cycle. This is almost true. There are also blue giant stars, as we can see in this picture here, the ones up here. These are as large and way more luminous than the red giant stars. And these are actually in the beginning of their life cycle. These are main sequence or proto-main sequence stars, or as we shall later see for the most massive of them, it barely even makes sense to talk about them being on the main sequence, because their lifetime, when we reach these really high masses, are so short that they are actually shorter than the time it will take for them to settle down on the main sequence in the first place. But these blue these blue giants and supergiants and hypergiants are extremely rare. They're also extremely luminous, so they are not unimportant. But number-wise, they are extremely rare, and the red giant stars are way, way more luminous. So statistically speaking, what I said here still holds true. When we are studying stars, we are very often using the sun as a reference for everything we measure in other stars. And that is simply because the sun, being by far our most proximate star, is also the one we know the best, we understand the best. It simply makes sense to use that as a reference, especially because if we later learn new things about the sun and we have done all our measurements of other stars in units or in terms of what the sun is, then that new knowledge about the sun will automatically carry through to our understanding of these other stars. So there are many good reasons to do this. We often use the little symbol that you see here, the circle with a dot in it, as a symbol to refer to the sun. So what we see, for example, here means the solar radius, the solar luminosity, and the solar mass. In this slideshow, I have given them each their color, so they are a little bit more easily distinguishable. Observing stars. What is there actually to observe, and what can we learn from them? How can we interpret correctly what we learn and use that to also learn something about galaxies? Stars are black bodies, more or less. Stars are, to a very good approximation, black bodies. Black bodies are a kind of idealized body where everything is in equilibrium, and these bodies also do not reflect light at all, which is where they have their name from, black bodies or perfect black bodies. And it has been established that such black bodies are emitting radiation as a function of their wavelength, which is a very strong and also relatively simple function of their temperature. This has been established as Planck's law, as we see here, and we can see that it depends very strongly on its temperature. The higher temperature, the more of the integrated flux, as we see in the figure over here, is concentrated at short wavelengths in the very blue and ultraviolet end of the spectrum, where, on the other hand, if the temperature is lower, it is more evenly spread out and tends to be spread way more towards the longer wavelengths. The peak wavelength of a black body spectrum is governed by Wien's law. This is the wavelength at which this spectrum has its strongest intensity. And as you can see, it depends quite simply on the inverse of the temperature. So it is basically a 1 over x dependency, which should tell us that that this dependency is quite strong. If we have very high temperatures, then we will get a very low peak wavelength. And if we have a very low temperature, we can get very long peak wavelengths. If you look at the figure over here, let me just move myself. If you look at the model spectrum of the blue star of 10,000 Kelvin, you can see that it has indeed a blue peak wavelength at around 3,600 angstroms. If you look at a star which has the same surface temperature as the sun, of 6,000 Kelvin, you can see that it has a wavelength of around 4,800, 4,900 angstroms, which actually corresponds to not a yellow, but a green color. So we're used to calling the sun a yellow star or a white star, but technically speaking, it is a green star. Our eyes are just not very good at seeing this, because if you look at the difference in intensity between the blue and the green and the red end, it is not super strong. And it's quite overwhelming to all our different light-sensitive cells in our eyes anyway. So we see solar light as white, because the distribution is relatively flat within the range of our eyes. But technically speaking, it is green. You can also see, which is a little bit interesting, that the difference in peak wavelengths between the yellow and the red star, or the green and the red star, technically speaking, is a good deal larger than between the blue and the yellow star, despite the fact that the difference in temperature is only half that. So that is exactly what we would expect from this 1 over T dependency from Wien's law. Finally, we can see here that the luminosity of such a spectrum is given by Stefan Boltzmann's law. And it depends on the radius squared, which basically that's just the projected area pointing in our way. So it's not so strange. Larger area means larger luminosity. But it also depends on the temperature to the 4th power, which goes to show what we could already kind of glean from the figure over here, that the integrated output, energy output from a high temperature black body is much, much higher than from a low temperature black body, and it depends very sensitively on the temperature. I should also say here that the temperature is the surface temperature of the stars, and that leads me to become a little philosophical here, because the sun has a surface temperature of 6,000 Kelvin. It has a core temperature of several million Kelvin. And if you think about it, the sun is not very large, not for such a colossal difference in temperature, such a colossally steep temperature gradient between the center and the surface, which, I don't know, maybe it's just me. I haven't been used to thinking of stars and stellar atmospheres like that, but the sun is actually an incredibly efficient heat insulator. Anyway, enough of that. Moving on to some actual real stellar spectra, as we can see here. Here we have a row of 1, 2, 3, 4, 5 stellar spectra. And you can see they are representing very different stars. We see them from the top to the bottom, going from lower to higher mass, lower to higher temperature, and lower to higher luminosity. But you can actually still see the overall blackbody spectrum shape of this. This one here is jagged and broken up, but you can kind of still see it. Just need to remember that this one is so blue and so red and has such low temperature that the peak wavelength is actually out here outside of the range of this plot. But as you see, we go towards more massive, brighter and hotter stars. You can see that the peak intensity moves towards the bluer and eventually towards the ultraviolet wavelength. You can also see that there are a lot of absorption features from the stellar atmospheres in these spectra. And you can also see that these absorption features come from very, very different ions. This one here comes from molecules and metals and so on. Here it comes from some medium mass atoms and so on. And when you come up to the hottest stars, then most of this absorption is from hydrogen and helium. And these differences in absorption lines is exactly what has laid the foundation or been the reason for people creating the classification scheme of stellar spectral classes. We designed these different classes with the letters these stellar classes with the letters O, B, A, F, G, K, and M, moving from the brightest blue giant stars here in the O class and to the coolest, faintest red dwarfs here in the M class. And then after this scheme was devised, we have also discovered even more classes, even cooler and fainter classes of ultra-faint red dwarfs and brown dwarfs. And these have then gotten the classes L, T, and Y, so those have been added to the scheme afterwards. But the classic classification scheme is the O, B, A, F, G, K, and M stars from blue giant to red dwarf. And as you can also see here, that hot stars are by far dominated by the blue and ultraviolet colors, and also dominate the blue and ultraviolet colors. The fainter, cooler stars don't really emit much out here. On the other hand, out in the red, the light is dominated by the cooler stars. Again, this is in part because a larger fraction of the spectrum is emitted out in these parts of the spectrum, but also simply because there are more of them. Because if it was just one-to-one star, even at the same mass, the blue would still outshine the red star even out in the red end of the spectrum. But because there are so many more red than blue stars, this is not the case for an actual stellar population. The next step in classification of stars and stellar population has come with the Hertzsprung-Russell diagram. Basically, people found out by studying stars, here, now you can see it. Basically, people found out by studying stars, wait a bit, did I? No, that's fine. By studying stars that if you plot their surface temperature against their brightness, it is not random where they fall. There is some very clear parts of this diagram that are very heavily populated, and there are parts of this diagram that are completely or almost completely empty. And of course, this holds this fact that there are some regions that have stars in them and some regions that don't tell us something about the inner workings of stars. Most stars are found on the stable hydrogen-burning main sequence that we see here. Let me see. This one. So this is where stars sit when they are in their stable phase, when they are fusing helium into hydrogen. There is a balance between the gravity and the radiative pressure that counteracts it. They don't evolve much as they sit there on the main sequence. On the other hand, once they run out of hydrogen, they will veer off the main sequence and up into this giant branch up here, where they will perform an incredibly complex and intricate dance before they finally either go supernova or settle down here on the cosmic graveyard as white and eventually as black dwarfs. Looking at actual data, we can see this. This is a diagram of millions of stars measured by the Gaia satellite and the Gaia collaboration stars in the Milky Way. And we can see again that there is this very, very strong and pronounced main sequence, but you can also see that there's a bunch of stars that have peeled off and started out on this branch here, which is actually more like a tangle of a number of overlying branches, evolutionary branches that stars are moving and dancing around on here that all together come together to be this weird shape we see here. And finally, there's a bunch of white dwarfs that we see here. One thing I think is extremely cool about this data set is that there are so many stars that if you squint, at least I imagine this, you can actually even see a little trail of stars that evolutionarily are already dead, but not quite have gotten to the graveyard yet down here. For practical reasons, we often use a so-called color magnitude diagram rather than the classical Hertzsprung-Russell diagram. That is simply because the color magnitude diagram is much easier to measure than the actual temperatures of stars. A lot of other things than just the color of a star goes into measuring its temperature, but they correlate with each other. So oftentimes it is enough to just have some kind of color index of the star, and it will basically show you the same information as the temperature does, although maybe with a little bit more scatter, a little bit more mess introduced into the picture. But for a group of stars that are at the same distance, for example, a stellar cluster, this color magnitude diagram basically shows the same information as the Hertzsprung-Russell diagram. And one thing that is particularly cool is that if all these stars also have the same age, then you can actually see how, as in this case here, how these stars are kind of peeling off the main sequence. So this is the break-off point. Below this, the stars are so low mass that they have not yet run out of hydrogen, so they still sit on the main sequence and populate it very densely. Whereas up here is virtually empty because all the stars that were younger than a certain age, that are more massive than a certain mass, have already run out of hydrogen to fuse and started fusing helium and heavier elements and gone up to the giant branch, or rather the giant branches up here. And that means that if you can measure this breakoff point here, and you know that you have one single stellar population that are formed at the same time, then you can basically measure the age of this population with a very high accuracy. And that is exactly what you have when you look at globular clusters. This is the M3 globular cluster, which is a cluster of hundreds of thousands of stars in the Milky Way, which have all formed at the same time. And because it was so dense, they have stuck together. They have not gone scattered like smaller clusters often do. And that means that we are looking at a bunch of stars that are all born with the same metallicity, all born at the same time, which means that this diagram can give us an invaluable look into the evolution of such a population. By the way, the number M3 here shows us it is from Charles Messier's catalog of pesky comet imposters. So I just thought I would show you what such a pesky comet imposter looks like. Here it is. Poor Charles Messier. So before we end for today, we should also have a little look at the physics of stars. Again, this is knowledge that it is assumed that you already have, but nobody's hurt by having a little recap of it, so we know that we're all on the same page. Stars are big balls of gas and plasma that is in hydrostatic equilibrium and is fusing nuclear and is fusing atomic nuclei into heavier atomic nuclei. That is basically what defines a star on the main sequence. They consist of fractions of hydrogen, helium, and trace amounts of metals. These fractions are mass fractions, and these are conventionally called capital X, capital Y, and capital Z, or capital Z. As you probably know already, in astronomy, anything that is heavier than helium is considered a metal, including very metallic metals such as oxygen, chloride, xenon, argon, and carbon. But its convention, it is convenient. It's a convenient way to lump these things together, which we do for good reason. They together are still, even after billions of years of chemical enrichment of the universe, still only a very small percentage of the mass of the universe, which is completely dominated still by hydrogen and helium. Stars are in hydrostatic equilibrium. It means that the gravity inward is balanced by thermal pressure. And they can sit like that for a long time as long as they have a stable hydrogen fusion going on. That is why that they can pile up on the main sequence like that. This is a quite stable state to be in as long as they haven't run out of hydrogen. There is an upper mass limit to how massive stars can be. It mainly has to do with the distribution of sizes that a giant molecular cloud, the distributions of sizes of the smaller clouds that a giant molecular cloud breaks up into and eventually forms stars from. So stars are formed from giant molecular clouds, typically hundreds of thousands to a few millions of times the mass of the sun. And when these clouds cool down and break up, they break up into a distribution of smaller and larger clouds, and each of these clouds in turn contracts and forms a star. And of course, the distribution of larger, more massive versus smaller, less massive clouds eventually also ends up determining the distribution of larger, more massive stars and smaller, less massive stars. And from what we have already learned, that should also tell you that this also has a huge impact on the further evolution of the stellar population. If there are many very massive stars, then after a very short time, they will pop off supernova very quickly, and they will scatter a lot of the gas and lead to the creation of second and maybe even third generations of stars, while the lightest, least massive stars are still forming. On the other hand, if you have a distribution with a lot of low mass stars and not a lot of high mass stars, then you will see a completely different long-term evolution of the stellar population. So this distribution of sizes of the clouds that the giant molecular cloud breaks up into, this distribution of masses, which eventually determines the distribution of masses of the young stars at zero age, this is called the initial mass function. This thing here. This is perhaps the most important concept to take away from today's lecture. The initial mass function is, as you probably could already glean from what I told you, is of incredible importance to everything that has to do with stellar population and therefore also galaxy evolution on the longer term. And we will spend a lot of time, I promise you, a lot of time looking into the ramifications of this. And before I move on, I should also mention what was said here, that at a mass less than 8% of the solar mass, you don't get enough pressure to get the temperature in the center to get high enough to start fusing hydrogen into helium. So these small things can get quite hot, but they can never settle on to the main sequence. These stars become brown dwarfs, and brown dwarfs can have a rather high temperature. They can be rather bright in infrared wavelengths, but this is not because of nuclear fusion. This is simply because of the pressure on the stars from the gravity, which makes the temperature rise in the center. It's just the ideal gas law in action. Massive stars live shorter and spend shorter time in the main sequence, but how much shorter? We can see that, or we know from measurements that the luminosity is proportional to the mass to a power of a number alpha, which can be measured empirically. And we have found that this number sits somewhere in between 2.2 and 5 on the main sequence, for main sequence stars. So oftentimes we use a fiducial value of alpha to be 3.5, which is like an overall average of this distribution of numbers. And using that, we can find that using that the time that a star will spend on the main sequence in terms of the time the sun spends on the main sequence lifetime, is basically a product of the ratio of their mass to light ratios of the different stars. And you can use that plus this value, fiducial value of alpha, to find this dependence on mass and this dependence on luminosity. And in order to get an example, we can take a look at a star that is 10 solar masses, and we plop those values into these formulas, and we find that such a star spends only about 30 mega years on the main sequence. That is 0.3% of the time that the sun is expected to spend on the main sequence. You can probably then guess that that also means that a star that is 1/10 of a solar mass, for example, can spend incredibly long on the main sequence. The lightest red dwarfs, we can only guess what their typical lifetime is because it is many times the current age of the universe. There simply hasn't been any red dwarfs that have run out of hydrogen to fuse yet. So we can only guess. On the other hand, you can also imagine how short a 100 solar mass star would spend on the main sequence, if it even makes sense to talk about the main sequence for a star that lives for such a short time that it can barely even have time to settle down on the main sequence before it dies. If we take a closer look at the stellar evolution after they peel off the main sequence, after they have run out of hydrogen to fuse, we can see that their evolution after that stage depends very, very sensitively on their mass. Here are some calculated evolutionary tracks in the Hertzsprung-Russell diagram. So we still have temperature here and luminosity here. And you can see that these stars all are stars that are born with a metallicity of 2%, which is rather close, a little bit larger than the metallicity of the sun. And the only thing that is different between them is their mass. We have 0.8 and 1 solar mass stars down here. We have 25 and 40 and even 120 solar mass stars up here. And you can see that their evolutionary tracks basically have nothing to do with each other. What exactly happens in the late stages of their lives depends so extremely sensitively on their mass. But it also depends quite sensitively on their metallicity. So here we have a similar set of computed evolutionary tracks, but here for two different metallicities. So the blue tracks here, they show they show tracks for a population of stars of 0 metallicity, while the red tracks show the evolution for a population of stars with similar to solar metallicity. And you can see that here we have stars with 3 solar masses. Here we have stars with 5 solar masses. They follow each other reasonably well right at this like intermediate mass range. But both below and above, it is a big old mess. And you can see that even the main sequence itself doesn't fall exactly on the same place in this diagram, because so many things behave differently when the metallicity is different. So when we can start varying both the metallicity and the mass of the stars, of course, this gives room to a lot of variety, a lot of diversity, and a lot of complexity in the behavior of these stars as they go through the end of their life cycles. Stars are the source of almost all elements that are heavier than helium. And therefore, it is interesting for us to know what these mass fractions of hydrogen, helium, and metals were right after the Big Bang, before any stars had formed yet, because that, of course, can also teach us something about how efficiently stars turn hydrogen and helium into heavier elements. What we know at this point is that right after the Big Bang, the universe by mass consisted of roughly 75% hydrogen, that's the number X here, around 25% helium, and trace amounts of lithium, and virtually no elements that were heavier than lithium. Today in the sun, we know that the hydrogen fraction is down to around 70%, and the helium fraction is up to around 30%, while the metal fraction is up to around 2%. The sharp viewer will note that this adds up to more than 100%. That is why we have these squigglies here instead of actual hard equality signs. There has been some rounding going on, but the main story is that on the order of magnitude of 5% of the universe's mass has been turned from hydrogen and into helium during the about 14 billion years that the universe has existed, and about 2% of its mass has been turned into heavier elements. So it's going slowly but steadily forward. The solar metallicity is, I said, 2%, it is 1.8%, but that's close enough. That is often also expressed in this alternative way that you see here. This way is basically based on the ratio between oxygen and hydrogen, rather than if we were to measure the metallicity correctly, the right way, we should really measure the abundance of every single element in the periodic system. But of course, that is not something we can practically do, especially because any tracers of these elements that we can observe are usually very, very faint and become impossible to observe, sometimes even within our own Milky Way. But oxygen is different. Oxygen has some emission lines particularly that are extremely bright. They can even compete with the emission lines of hydrogen in star-forming galaxies, even though there's way, way more hydrogen in these galaxies. And that makes oxygen very easy to observe, even at high cosmological distances, even at like billions, even like at redshifts of 10 or 20, like a few 100 million years after the Big Bang, we can still observe oxygen. And that means that we can use that as a proxy for the metallicity of the universe at those ages. We need to make some kind of assumptions about, or have some kind of models of the relative abundances of oxygen to other heavier elements. Of course, you cannot just use these relative abundances like you would in the sun and say, well, it's probably the same in the early universe, because it wasn't. We need to have some kind of model for it. You can also see that it is expressed in this slightly awkward way with a 12 plus the logarithm of the ratio of oxygen over hydrogen. And that is simply because it's convention, it's practical. It gives us nice numbers that typically sit between 5 and 10. And we like having numbers that sit between 5 and 10 instead of having numbers that are way less than 1 or way larger than 1. So it's just that, a convenience. It seems a little weird to begin with, but you get used to it, and I would say get to appreciate it over time when working with it in practice. Finally, a couple of discussion questions that I will ask you to think a little bit about, mull over in the back of your heads until we meet on Monday, where we will discuss them in class. There are 2 questions, and I will read them aloud now. First is question A, that says, how would you go about constructing a model spectrum for a galaxy? For this exercise, you may assume that the galaxy consists only of stars. What other assumptions do you have to make? And what would the difference be between a young and an old galaxy in terms of how the model would be created? And I would add, in terms of how the spectrum would look, the resulting spectrum of that model. And question B is, if we observe a galaxy to be very blue in color, even dominated by light emitted by the ultraviolet, What conclusions could be drawn on its content and its properties? Think about that till we meet on Monday. And yeah, that's it. That's it for this time. That's all I had. I will see you around the next time. Thanks for hanging on till the bitter end. If you did, but I assume you did, because otherwise you won't hear this. Whatever. Bye for now.